Professor, I hate to interrupt, but I think you're muted.
Thank you for letting me know that. Made an announcement saying that we'll cover mesh current analysis today, and I was just doing a brief recap. So thank you for letting me know. Okay, so as I was saying, we generate equations in this technique by applying KVL. KVL means we are summing up voltages around a loop. The unknown variables in this technique are the mesh currents. The mesh currents are not real, they're hypothetical. We assign them at the beginning of our analysis. We choose a direction for them. And then we write our KVL expressions and apply Ohm's law to express each voltage drop or each voltage in terms of the mesh current itself. Okay. So as a recap, the node voltage analysis and the mesh current analysis techniques, they are new, but only a portion of the concept is new. Okay, the application is not new. It requires KCL and KVL. KCL and KVL is something you have studied in the past. You also studied it in the first 2 weeks of this quarter, right? At the beginning of this class. That is specifically the reason why I assigned those homework at the beginning in the first week, because students need to know how to apply KCL and KVL. Okay, so we simply apply KVL in here in mesh current analysis. Prior to that, the concepts that you learned, those are the new material. That's the new topic. How to apply KVL is not new. Okay, setup of the problem is the most important. So that's where I want students to let me know if they have any questions. Okay. So any questions about applying KVL and generating our equations for mesh current analysis? Let's do a brief recap. How many meshes in the circuit? 1, 2, and 3. Identifying meshes is easier than identifying nodes because it's a closed pathway, and the closed pathway does not have any other pathways inside it, right? So it's a mesh. A mesh is a closed pathway, does not have any other pathways inside it. 1, 2, 3, 3 meshes. I label them. We have assigned currents, I1, I2, I3. Typically, I would simply choose clockwise direction for all 3 mesh currents or all the mesh currents in the circuit. Once you have a clockwise direction, you apply KVL around each individual mesh. In mesh 1, which I've drawn out here, I have 3 components: voltage source VA, resistor R2, and resistor R3. VA is the voltage source. The value would be known to us. We simply write out the expression for KVL, using KVL. So we have VA plus VR2 plus VR3 equals to 0. You apply KVL with the technique that you're comfortable with. You do not have to do this. Okay. Typically, what you might be comfortable with would be VA minus VR2 minus VR3. The equation is still the same. That doesn't change. Okay, the equation remains the same. Anyway, so you have minus VA plus VR2 plus VR3 equals to 0. Then you apply Ohm's law. And when you apply Ohm's law, you can express each resistor voltage in terms of the mesh currents. So you have plus I1 times R2 plus I1 times R3. But we also have to account for the mesh currents shared between a branch. And so for R2, it is R3, it is I3. And so it becomes I1 minus I3 for R2. R2 is the resistor up top. It is shared between 1 and 3. And so we account for VR2 and VR3 because they're both in a shared branch. We have I1 minus I3, and then you have I1 minus I2. Those are the most important points when you're applying mesh current analysis. If you know how to do that, then everything else is easy. Yes. It would flip. So the question being asked is if the currents were counterclockwise, then the signs would just flip. So the signs come from the fact, well, the rule, the fact they never change, right? If current flows through a resistor, point of entry is plus, point of exit is minus. So it comes from those rules. So if you take R3, for instance, right? We have R3, we have shared I1 and I2, right? Shared branch, which has I1 and I2 flowing through it. If I1 flows through R3 coming from the top, what is the voltage polarity due to I1 at the top? Point of entry, point of exit, minus. How about for I2? Top node is plus or minus? Just one student. Let's take a pause, think on that, let me know. Current flows through a resistor, current flows from high to low. If both ends of the resistor have the same potential, no current will flow. One end has to be higher. So current always flows from plus to minus. Conversely, point of entry is always plus. So if I2 is entering R3 from the bottom is plus, top is minus. Those two voltage polarities that I noted right now are not real. They are hypothetical. You cannot have one point or one end of the resistor higher and lower at the same time, right? Physically impossible. Again, they are not real because the mesh currents are not real. But in mathematical analysis, when we make an assumption about the mesh current, we can also make an assumption that the current would result in a voltage. Those voltages would have the same polarity, or they will follow the same rules for currents and voltages, meaning point of entry would be plus, point of exit is minus. So two hypothetical mesh currents would cause two hypothetical voltages to appear in that same resistor. That's where this conclusion comes from. If you now add up these voltages, one of the voltages is plus VR3, the other voltage is minus VR3. Let's take a pause while you think on that and let me know if you have any questions. Does that make sense though? While you're thinking on it, hopefully it will. Does that make sense? What if both the currents were in the same direction through that resistor? Meaning at the beginning of the analysis, we choose I1 to be clockwise and we choose I2 to be counterclockwise. What would we have now? This remains the same, obviously. How about on the right side? What is at the top? Plus, minus. So now my equation would be, if I was to apply KVL in mesh 1, both currents are positive, both voltages are positive. And so I would have I1 plus I3 times R3. This would be for mesh 1. If I go to mesh 2 and apply KVL, that same voltage VR3 would become Does that make sense? Because now you're summing up voltages in the other mesh. The mesh current directions don't change. They remain the same. So now when I sum up the voltages, I'm going in the opposite direction. So it'll become minus and minus. Both voltages would end up being negative. So think on that. Let me know if you have any questions. Yes. Well, the voltage polarity. So the question being asked is, can we change the voltages in each individual mesh? The answer would be no, because the voltage polarities appear due to the chosen direction of the mesh current. So if the mesh current direction does not change, then the voltage polarity does not change. And that's the beginning of the analysis, right? If we assume a mesh current and we assume a direction at the beginning of our analysis, we do not change halfway through the solution. And so then the voltage polarities would not change. They would remain the same. So if you have an assumption where I1 is clockwise, I2 is counterclockwise, then you have a double positive in mesh 1, and correspondingly, you would have a double negative in mesh 2. The equations will still balance out. Does that make sense? Hopefully. Shall we go on to the example? Okay. Oh, I always forget the summary slides. All right. 3 steps. First thing is identify the meshes, assign mesh currents to each mesh, assume a direction, whether clockwise, counterclockwise, does not matter. Then you apply KVL to each mesh. Once you have KVL, you'd have the number of voltages in there. The number of voltages or the number of terms in your equation should match up to the number of components you have in each mesh. And then you apply Ohm's law and express each resistor voltage in terms of the mesh current. If it's a shared branch, then I would say stick with clockwise directions for every single mesh. That way, if you're in mesh 1, you take I1 as positive. If you're in mesh 2, you take I2 as positive. I mean, I1 as negative. Okay. Let's go here to the example. How many meshes do we see? How many loops? How many electrical loops do we see? 1, 2, or 3, or 4, or 5? There's only 2 meshes. Meshes are easier to identify. And there are only 3 loops. There's no other pathway for current to flow through. So 3 loops and 2 meshes. Again, meshes are easier to identify than nodes. So we'll call this M1, and this is M2. We'll assign a clockwise mesh current to both and label them as IX and IY. Okay, IX and IY. I'm going to draw out mesh 1 on the right. Okay, this is R2, VA voltage source, VB voltage source, R1. And I have IX going in a clockwise direction, causes the voltage drop here and here. And I also have IY on the other side. How many of you have MATLAB on your smartphones? Anyone? No one? How many of you know how to solve a system of linear equations on MATLAB? 1, 2, 3, 4, just 4, 5, half a dozen, hopefully. All right, I will show you the steps. It's not that difficult. It's only about a 3-step answer. So again, if you have a programmable calculator, you can program equations in there. It'll give you a direct answer. If you have access to the internet, during the quizzes you do, you can program the equations in an online solver. Or if you have MATLAB on your smartphone, program it into your smartphone or tablet, and then it will give you an answer. Okay. So we'll apply KVL, we generate our equations, we'll have 2 equations, and then we'll solve them. Okay, so mesh 1. How many components do we see? 4 components. My eyes are not that good, so if you show it like this or like this, I wouldn't be able to tell. Some students were showing like a, like a 4 close to their chest, and I was like, I have to squint to actually make out. My eyes haven't been good since I was 12. So, how many components? 4. 2 voltage sources, 2 resistors. So there should be 4 terms in my equation. Okay. I will write out VA, VR1, VB, and VR2 should be equal to 0. Because of the way I apply KVL, my resistors will always have a positive polarity. If I start from the bottom left node and I go clockwise, summing up the voltages, I get VA as negative, VR1 as positive, VB as positive, and VR2 as also positive. If you have a preferred technique, again, I'm repeating the same thing. You have a preferred technique of applying KVL, you stick with that technique. You don't have to use mine. Just ensure that our equations match up. Okay. Do you have the same equation? Okay. All right. Now, so this is KVL. And the next step would be to apply Ohm's law and express each resistor voltage in terms of the current. R1 is not shared, right? So this would still remain VA. R1 is not shared. It simply has IX times R1. VB is a voltage source, so we write out VB as it is. R2, the resistor R2 is shared between 1 and 2. You have IX and IY. Since I chose clockwise for both, I can simply state if I mesh 1, IX is positive, IY is negative. And so I can write IX minus IY times R2 equals to 0. Okay. IX minus IY times R2 equals 0. And again, when it comes to shared branches, this is the most critical step. The actual solution doesn't take long. 3 steps and you have your equation. Okay. But applying KVL and then expressing the equation in terms of Ohm's law, that's the most critical part. And that comes from the assumptions you make at the beginning of the problem. So setup of the problem, and then the first 2 steps, that's most of the work. Okay, that's most of the work. And now I have that. I would enter the values. VA is 10, so I would get minus 10 plus IX times R1. R1 is 5. VB is 9. And I'm going to open this up. So this is IX times R2, which is 10 minus IY times R2, which is again 10. Reduce the expression to the form of AX plus BY is equal to C, and you would obtain 15 times Ix minus 10 times Iy equals 1. And I will label this equation as equation 1. Okay. Keep in mind that the number of resistors you have should equal the number of terms you have in your, well, actually, I'm saying that the other way around. The number of terms you have in your equation should equate or should equal the number of resistors you have. What I mean is Ix flows through R1 and R2. Ix is flowing through R1 and R2. So in my equation, I should have 2. Make sense? Right? If you don't have 2, then, well, there's an error in your circuit. Does everyone see what I'm saying? Right? Ix is flowing through R1 and R2. So when I have my equation, I should have 2 terms for Ix. All right, questions? Okay, let's get to mesh 2. Mesh 2, we have R3, 2 voltage sources, and 3 resistors. VB, VC, R2, R4. This is IY. This is IX. Plus, minus, plus, minus, plus, minus for R3. And I am ready to apply my KVL. We ready to apply KVL? 5 components, so 5 terms in my expression. Starting from the bottom left corner, I have VR2, VB, VR3, VC, and VR4 should be summing up to 0. All my resistor voltages are positive. So VR2 minus VB plus VR3 plus VC minus plus VR4 equals to 0. Did you obtain the same equation? That doesn't matter how you apply KVL. The answer will always be the same. Okay. All right. Once we, yes. So the technique I use is basically, as you saw me, I write down the components that the voltages that I have in there, and then I start from the bottom left corner and I go clockwise around the loop. I mark the voltage polarities. Each voltage, the sign that I encounter first is the sign that I place in my equation. If I start from the bottom left corner, VR2 is positive, VB is negative. Okay, next step is apply Ohm's law. So this was KVL. Apply Ohm's law and express each resistor voltage in terms of the mesh currents. Here I would have IY minus IX because R2 is shared between 1 and 2. In equation 1, excuse me, in mesh 1, it was IX minus IY. Now it's IY minus IX times R2 minus VB plus IY times R3 plus VC plus IY times R4. Not stop talking for 3 hours. Excuse me. Okay, so now we plug in the values. R2 is 10 ohms. So IY times 10 minus IX times 10. VB is 9 volts. R3 is 5. VC is 1. And R4 is also 5. Rearrange the terms, reduce it, and you obtain an expression minus 10 times IX plus, now IY flows through 3 resistors. So you have 3 terms for IY, which is 10, 5, and 5. So 20 times IY is equal to 8. I'm going to label this as equation 2. You plug it into your calculator, into an online solver, solve it manually, or as I'm going to show here, how to do using MATLAB. You define a variable, random variable. In your workspace, you're going to type up the constants. So A equals, in straight brackets, from equation 1, I have 15 and minus 10. There should be a space between the two constants. Then for equation 2, you program, you have to separate it out using a semicolon. This is not a J. Second equation, the constants are minus 10, space 20. Close the bracket, press enter. What it will do is it will put these constants in a 2 by 2 matrix. Then you define B. B is 1 and 8. Press enter. Again, put it into a matrix. And your answer C should be A backslash B. That gives you the answer. That's it, as easy as that. Students who know how to do it, do you perform the calculation this way, or do you use a different method? That's about it. Yeah. So 3 steps. Your calculator is also something pretty similar. You enter the constants in there, you program it, you press answer, and it should give you the answer. So again, as engineers, these are all tools at your disposal. You can solve it manually. You can solve it using software tools, use an online website, program it into your calculator. There are multiple ways to solve this. You should know, as an engineer, you should know how to use each and every one of those. Okay. So on the quizzes, you can use an online website if you wish, but on the final exam, there will not be an internet option. Okay. It'll still be open book, open notes, most likely, the final exam, but I might not allow internet yet. So I'm thinking about it. Yes. You can use that. Yeah, that's fine. So again, that's why I was recommending students or suggesting to students that install it on your smartphones. It's just a fun and convenient way to actually use it everywhere we go. So if you don't have your laptop with you or your tablet with you, you can still use the app and get the job done. Anyway, solving this manually, let's take equation 1. Equation 1 times 2 gives me let's see, equation 1 is here, 15 times ix, 10 times iy, so it gives me 30 minus 20 and 2. Okay, so 30 times ix minus 20 times iy is equal to 2. This is what I would obtain, and I'm going to label this as equation 3. Equation 2 plus equation 3 gives me 20 times ix equals 10. So ix is 0.5. For students who solve this, do you have the same answer as I do? Anyone? Solve it? How about the value for iy? What did you obtain for iy? 0.65. That is correct. And of course, once you have the value for ix, you can plug it into any one of those 3 equations and you can obtain a value for iy. So again, if the equation is simple enough, you can solve it manually, which is the method I prefer typically. Otherwise, you can plug it into your calculators, online, software, any tool you want. Okay, questions? Does the method make sense? Applying it step by step. Ask yourself the questions. How many meshes do I see? Then choose the current direction. Take it one mesh at a time. Once you apply KVL, how many components are there in each single mesh? That many voltages should appear in your equation. Once you have that, you plug in the known values, express in terms of Ohm's law, and reduce the expression. It's the shared branch concept that is usually the place where I see the most errors. Okay. So to keep things simple, choose clockwise directions for all currents, all mesh currents. And that way, when you sum up voltages, you simply take the mesh that you're in, you take that current as positive. Any currents outside that mesh will be negative. Yes. So the question being asked is, how do we choose which method to use to analyze a circuit? So let's say I'm an engineer, I have a large circuit that I'm trying to analyze, and I'm trying to decide between node voltage or mesh current. In both cases, so here's the answer. In both cases, what are we trying to do? We are trying to generate mathematical equations. The equations will have terms. So there is no right or wrong answer, right? I might start with node voltage and it might turn out that mesh current is easier. So that's just the way it is. But again, the work as an engineer is to be as efficient as possible while minimizing the cost to your company. Companies always are all about minimizing costs, right? That means the most efficient method. You minimize cost, that's the most efficient method. So efficiency in this case would mean trying to solve equations that have the least amount of variables. So node voltage versus mesh current is always a case of identifying the meshes and identifying the nodes, because the number of nodes is the unknown variables and the number of meshes or the number of mesh currents is the unknown variables. In this case, if you take a look at this example, how many meshes? 2. So 2 meshes, 2 mesh currents, 2 unknown variables. So 2 equations. How many nodes do we see? Someone says 6. Can we reduce any of them? No, there's nothing that is in series. There's no resistors in series. There's no resistors in parallel. So we cannot reduce it. Counting from the bottom left corner, the bottom node is 1, 2, 3, 4, and then 5 and 6. The answer is correct. It's 6 nodes. Even if I choose the bottom node as my reference, I have the answer for the top left node at VA. Out of 6 nodes, I have eliminated only 2. That still leaves me with 4 nodes, 4 unknown variables. I would need 4 equations to solve the circuit using node voltage analysis. Versus mesh current analysis, I only need 2. And that is the answer. We would go with whichever variables, whichever circuit or whichever method has the least amount of variables. And then also it also depends on whether it has voltage sources in there or whether it has current sources in there. That is also a factor in consideration. Make sense? Right. In the exam or the quiz, I will explicitly state you have to use node voltage analysis to solve for this, or you have to use mesh current analysis to solve for this. There is a specific reason for that. We are required to teach you certain topics, right? And then we are required to assess your knowledge and understanding of that certain topic. So if I ask you, show me using this method, but you solve it using another method, then I have no basis for assessment. If I ask you about node voltage, but you solve it using superposition, I cannot judge your understanding or knowledge about node voltage. So I cannot give any points to that problem. It's as easy, as simple as that. Okay. So if the question states solve using a particular method, you have to use that method. Otherwise, I have no basis for assessment. All right. Any questions? Okay. Then let's look at what a super mesh is. Super mesh, like super node, is simply a shortcut. And it comes, we have to have that approach due to the fact that a current source cannot be described. I mean, the voltage for a current source cannot be described. We can say that the voltage across that current source is, let's call it Vx. Let's call it Vx, random variable. Then that is an unknown variable which I cannot describe by any means. So I have to eliminate that variable from my equations, right? If I apply KVL in mesh 1, I have 1 ohms, 2 ohms, and then I have Vx. What to do about Vx? Can't do anything. So if you have a current source in a shared branch, what we can do is we can ignore the current source and combine the 2 meshes together. So we have mesh 1 and we have mesh 2. We ignore the current source, we combine the 2 meshes together, and we apply KVL in the outer loop. The concept is the same as the supernode concept. In supernode, we had a voltage source. We apply KCL at either end of the voltage source, and you ignore that voltage source in the middle, right? We combine both of those together. And so we're doing the same thing. We have mesh 1, we have mesh 2. They are sharing the current source in the middle. We combine both of them together, and we apply KVL in the outer loop. Yes. That is correct. That's a very good question. So the question being asked is, if we had a resistor in the branch, as we saw in the previous example, if instead of the voltage source VB, if we had a current source in there, then what should we do? The concept still remains the same. We can still apply KVL in the outer mesh, but we won't apply to the individual meshes. Okay, so current source that is shared between 2. I will draw out the circuit by combining the 2 meshes together. So then this is 2 ohms, 4 ohms, 1 ohms. And here's the important part. We made assumptions at the beginning of our problem. Mesh 1 has I1, mesh 2 has I2, as shown in the example. Those currents do not change. They are still the exact same. So you still have I1 flowing on the left side, and you have I2 flowing on the right side. Again, this is a theoretical analysis. Okay, so it might seem as if I1 and I2 are the exact same, but they're not. Okay, all we are doing is we are applying KVL to the outer loop, but we still have to take into account all the exact same currents that we assumed at the beginning of our analysis. Also, we have the 2 ohm and the 4 ohm resistors in a shared branch. So we have to account for I3. Okay, you have to account for I3. So if you apply KVL in that outer loop, how many components do we see? 4, 3 resistors and a voltage source. And so I would have I1 times 1 plus I1 minus I3 times 2 plus I2 minus I3 times 4 plus 10 is equal to 0. That would be my KVL expression. Okay. We still have to account for the shared branches. We have I1 going clockwise and I2 going clockwise in mesh 1 and 2. We have to keep those as they are. Mesh 3, we have I3 going clockwise. We have to account for that also. Let me know if you have any questions. Any questions? Yes. Bottom outer loop and the top mesh. Yes. That is going to be the next point that I make. It'll be there. Yeah. Good question. So we have 3 unknowns, I1, I2, and I3, but we only have 3 equations. So what can we do? Well, the answer lies. Let's look at first what happens, or well, actually, you'll tell me what to do if you have a current source that is not shared. So we have a circuit here. You have a current source that is not shared. Yes. That's it. Okay, the question is what can we do about IS that is not being shared? Well, similar to the reference node and the voltage source, if we choose a mesh current IY, that's the only current that is flowing through that current source IS. I can simply state that IY is equal to IS. The magnitude will be the same. The sign would depend on the direction of the mesh current and the direction of the current source. If they are both in the same direction, the sign is positive. If they're in the opposite direction, the sign will be negative. In this case, IY is opposite of IS, so it will be minus. So if it's not shared, we can simply assume a direction for the mesh current and assign a value to it. And that eliminates one unknown variable. You only have one unknown variable left in the circuit. You need one equation, and that's it. Does everyone understand that? Right? And that leads me to point out, well, I not point out, but ask, how can you express this 5 amp source in terms of I1 and I2? Yes. It will be the sum of the currents, yes. So you have I1 and you have I2, which should sum up to 5 amps. Which one has the same direction as the 5 amp? I1 is coming down, I2 is going up, and so I2 has the same sign, I1 is negative, and you would simply write I1, I could write I2 minus I1 is 5. Or I can express, not or, and after this step, I can express I2 as equals 5 plus I1, or I can express I1 is I2 minus 5. I can express either I1 in terms of I2 or I2 in terms of I1. Then I can take that, plug it into the equation, I get rid of one more unknown. And that's how you can solve it with only 2 equations instead of 3. Does that make sense? Okay, homework for mesh current analysis is due tomorrow. There are 3 problems on it. Shouldn't take long, not longer than an hour at least, maybe hour, hour and a half. I will post hints similar to the ones that I posted for node voltage analysis. If you get stuck anywhere, come see me. I have office hours today. Tomorrow, I'm teaching from 8 to 6. I won't have time tomorrow at all. But you send me an email, I will be able to reply to that email. If you absolutely need to see me, come see me in room 126 between 8 and 3. I will be teaching in there. Okay? That's tomorrow. Even today, from 3 to 6. All right, I will see you all on Friday.